This bus did not carry a diesel engine. It did not have a giant battery. And it did not need wires hanging above the whole road. Instead, it ran on a spinning metal wheel. In the early 1950s, engineers in Switzerland tried to solve a problem that still sounds modern today. Cities wanted cleaner public transport, but trolleybus wires were expensive, batteries were limited, and diesel buses filled streets with noise and exhaust. So Oerlikon built a different kind of electric bus, the Gyrobus. At a stop or terminal, the bus raised 3 metal arms to a charging point. Electricity flowed in, and deep inside the vehicle a heavy flywheel spun faster and faster, up to about 3,000 revolutions per minute. Once it was charged, the bus could pull away without rails, without a diesel engine, and without staying connected to overhead wires. The idea was elegant. A motor spun the flywheel while charging. On the road, that same system worked like a generator, turning stored motion back into electricity for the drive motors. When the bus braked, some of the energy could be fed back into the flywheel. It was not magic. It was a mechanical battery. For short, quiet routes, that sounded almost perfect. A fully charged Gyrobus could typically travel around 6 kilometers on level roads, with speeds in the range of 50 to 60 kilometers per hour depending on load. Charging could take from about half a minute to a few minutes. Compared with wiring an entire route, a few charging points looked simple. The first full commercial service began in 1953 between Yverdon-les-Bains and Grandson in Switzerland. More Gyrobuses later operated in Leopoldville, now Kinshasa, and in Ghent, Belgium. For a brief moment, it looked like cities might get clean electric buses without covering every street in wires. But the future had weight. A useful flywheel was not small. It had to store enough energy to move a bus full of people, so it was heavy, it needed strong bearings, and it had to be mounted safely. At thousands of revolutions per minute, a flywheel is not just a spinning part. It is stored kinetic energy that must never come loose. The range was also short. Every route had to be planned around recharging stops. If traffic was heavy, roads were rough, or passenger loads changed, the margin got smaller. A delay at the wrong place could become an operational problem, not just an inconvenience. In Leopoldville, reports described serious wear and tear, bearing failures, humidity problems, and energy use that operators considered too high. In Ghent, the buses were judged unreliable and heavy enough to damage road surfaces. They were also energy-hungry compared with trams, which could carry more people for less energy per kilometer. That was the central contradiction of the Gyrobus. It was clean at the street, clever in engineering, and genuinely ahead of its time. But it tried to replace wires and batteries by carrying a heavy, fast-spinning machine through every corner, stop, pothole, and scheduled delay of daily bus service. By 1960, the Swiss service had ended. Ghent and Leopoldville had already moved on. Diesel buses were simpler. Trolleybuses were proven. Later, battery technology would improve enough to make a different kind of electric bus practical. Today, no Gyrobuses operate commercially. One restored Ghent vehicle survives in Antwerp, a quiet reminder of a path electric transport almost took. The Gyrobus failed, but not because the idea was foolish. It failed because storing energy is easy to imagine and hard to carry. Before lithium batteries became normal, before modern electric buses filled city depots, engineers tried to wind up public transport like a giant mechanical toy, and for a few years, it actually worked.